This little movie will take a car on a level road that will quickly go from 0 to 140 miles an hour, then come back to 0. And I'll look at the different forces involved. Notice the force of push is huge compared to the amount of road friction. And we're going to keep that force of push constant all the way up to 140 miles an hour. So this is why it quickly accelerates. Now at 20 miles an hour. At 30 miles an hour, we start to get a baby air drag here. We say 30 miles an hour in class. It's a generic car. Cars are different. Some cars, air drag is quicker, like on a semi-truck, or say a Tesla. It might take a little longer for air drag to become that noticeable. But for our generic car in class, we're saying that at 30 miles an hour. 40 miles an hour, little changes here. Notice that the normal and the EMG are congruent. If things are congruent, you have to show it. At 50 miles an hour for our generic car, we say that the road friction, which is basically mu sub s times normal force, and air drag are the same. It's just the rules of thumb. Also notice here at 50 miles an hour, you're starting to get a little baby uplift. I show the graph of air drag versus velocity. It goes up as a square of velocity. The formula is RA equals 1/2 d rho a v squared. We work problems on it and all, but I'm just on this. I wanted to show you how I got the length of my arrows. I actually used this, ran the parabola, and then dragged and dropped these arrows into the RA at each one of these velocities. So it does go up exponentially with velocity, and in turn then if you're speeding up with time. So it's going to eventually take over the road friction. In fact, at 50 miles an hour is where it takes over. I mean, basically just air drag is that the oxygen, nitrogen, argon, whatever's in the air, those molecules just can't get out of the way fast enough. The faster you go through them, the more of them there are to try and get out of the way, and it's just difficult to push all those out of the way. At 60 miles an hour, we say that for our generic car that you start to get a little lift. And we'll get to the formula for lift here in a minute, but the cart starts to lift a little bit. Still much more contact than lift. MG is much greater than lift. At 70 miles an hour, things are getting more complicated. Notice that the force of static friction, and it is static, we go through that whole thing, but between the tire and the road is going down, because that's basically the formula there is mu sub s times n. Well, as lift goes up, the amount of lift under the car goes up, the amount of normal force goes down. Well, if normal force goes down, then the road friction goes down. So plus the air drag RA is going up exponentially. Now at 80 miles an hour, 90 miles an hour, our air drag starting to dominate the horizontal forces. I base the length of my lift arrows on this graph, or on this graph that I made. This is a parabola again, because lift also grows exponentially with velocity. It's 1/2, instead of 1/2 d rho a, it's 1/2 c rho a, and that a is not the profile area, but the area of the wing. As the force of lift goes up, the normal force goes down. So eventually, you get to 160 miles an hour, and that's the point at which the normal force goes to 0, and the car leaves the ground. For this particular car, that'd be enough. You see videos of cars actually leaving the ground at high speeds. Now at 100 miles an hour. At 110, now lift is about the same as normal. RA continues to dominate. Lift finally, for this generic car, beats out normal at 120. forward road friction is going way down because it's tied at a normal force, the amount of contact. Finally, at 140, we are at the point where it's equilibrium in the X, meaning that no more velocity can be increased. So summation of force in that case is 0. The only way to go any faster now would be to somehow reduce the air drag, because the car is pushing as hard as it can. Notice there's still a little bit of contact. That's probably why the driver will have to back off, because at 160 that end's going to go to 0 and the car's going to lift off the ground. So already low amount of control on this car because so little road friction, so little contact with the road. So now we're going to start to slow down just by taking our foot off the gas initially. So here we go. Now we've taken the foot off the gas. Notice the only forward force, there is no forward force. The only force in the horizontal is air drag. 120, 110, 100. Notice air drag's dropping off quickly. 90. Here's 80. 70. And 60. And back to 50. So now the driver, instead of just letting off the gas and letting the car roll to a stop, the driver sees a squirrel on the road or whatever and slams on the brakes. And let's say these aren't anti-lock brakes, and so the brakes lock up on them. Then the FS turns into FK, which is considered sliding friction. And so let's see what happens there. Now notice you have a huge backwards force, F of K. No forward force, but you're still going forward because of inertia, or moving inertia, or momentum. Your direction of motion is still positive, but all your forces are negative. Okay, 30 miles an hour, 20 miles an hour. Now we've lost our air drag completely. Notice though that the normal force is not congruent to mg, and that's because you're slamming your car down. The front of your car is going into the earth is pushing back on you, and so the amount of contact is greater than the weight of the car while you're slamming on the brakes. Stopped again. Alright, now I'm going to do a series of going up and down faster to let you compare the arrows that you see and see how they change for the 140 miles. We're going to 0 to 140. So start at rest again, and we're going to quickly, with 1 second, go through all these. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140. Okay. So now I'm going to do it really quickly, now about 0.2 seconds per 10 miles an hour. And so you can just take a look. Notice the difference in lengths of the arrows, the lengths of the vectors, how they adjust. So this is almost a movie here. Starting back from rest, here we go. Hang on. Okay, now we're at 140. Let's reverse the process and go back down. Once again, look at the relative lengths of these vectors. One more time up and down, this time even quicker. This is the last round. Watch those arrows change. Alright, made it back to safety without getting into a wreck. So hopefully this helped you see how free body diagrams are really snapshots of what's going on in any particular situation. Thanks.